Well, hello, folks. Yeah, welcome back to part two. We're going to be doing the paper two of Higher Physics 2019. Yeah, I'm not going to mess around for any longer. Let's get cracking. Data sheet. Remember this, folks. It's a data sheet. You never know when you might need it. But yeah, every so often they'll ask you to call back there. Yada yada. Question one. A student carries out an experiment with a tennis ball and a motion sensor connected to a laptop. The ball is released from rest below the sensor. The graph shows how the vertical velocity v of the ball varies with time t, from the moment the ball is released until it rebounds to its new maximum height. Using information in the graph, show the initial acceleration of the ball is minus 9.8. So whenever you want to do this, it's always a good idea to have a look at the relationship sheet. I'll throw that in there. Right, and well, what do we know here? It's just the initial acceleration, so we want to calculate essentially this bit, right? So what we can write down there is, well, the initial velocity, that's going to be 0, right? It starts at the origin, it's nothing. And then its final velocity, that's minus 4.9. And then the time would be 0.5. Right, so if we go over to our relationship sheet, can we find an equation that works? Well, first one off the docket, well, third one off the docket, that seems to work right there. We've got velocity, we've got initial velocity, we don't have acceleration, but we want to work that out, and we have time. So what we could do is we could actually write down v equals u plus at, and then we'll plug in the numbers. But in case you're a bit confused, you don't like rearranging stuff, there's a popular rearrangement of the equation that you've probably seen before, which is a equals v minus u over t. And yeah, this is just brought about by rearranging that. You take away u from both sides and then you divide by t. But this just helps. I feel like this is kind of easier to understand. So if we plug in our numbers here, I've written a wee big, but it's essentially minus 4.9, take away 0 over 0.5. Now if I pull over my calculator, you should be able to work this out on your own, but just in case, because when you divide by 0.5, it's same as times it by 2, so you get negative 9.8 meters per second squared, which is exactly what we wanted. If I remember, put the 2 in, remember your units. But it won't matter too much because you don't get marks on the unit, your final answer. Obviously, if it tells you the final answer, probably a good idea to put it in even if you don't get it, but it gets marked on your workings. But anyway, that's that done. Determine the height from which the ball is released. So again, we can analyze what we've got. This time, we can add acceleration to our toolbox, right? So it's minus 9.8. If we go over here and look around for equations that have acceleration, initial velocity, final velocity, yada yada, there's a couple we could use. It's basically any of these. For this though, I'll pick the first one just out of randomness. I want to go over the middle one because you have to do rearranging to do that. It's not particularly difficult, it's just you want to have it as simple as possible, have the best chance of doing all your maths right. But this one down here is also completely serviceable as well. In fact, it might be preferable because if this wasn't a show that question and you actually had to calculate the acceleration, you didn't know what it would be, this won't be preferable because you wouldn't need to know the acceleration. But I'll just pick the top one. So S equals ut plus 1/2 at squared. Alright, well, what does that get us? So equals, the initial velocity is 0, time is 0.5, plus 1/2 times negative 9.8 times 0.5 squared. Boom. Now, making things easier on the calculator, you can actually ignore this first bit because 0 times something is just going to be 0 no matter what. So we can just go with the latter half, this next bit. So 1/2 is 0.5 times 9.8 times 0.5 squared. Bring that up and we get this number. Now, if you put your units in, meters, you can actually straight away get the mark. They're not going to take it away for you for leaving the minus sign, surprisingly, but I would recommend not having minus sign because it technically doesn't make it, negative displacement isn't really, it's valid in this case, but it's just a bit iffy in my opinion. I recommend you round it to 2 decimal places and like that and take a read by side. But in this particular scenario, you actually would get the mark for this thing here, but overall. Anyway, we'll move on to B now. The mass of the ball is 57 grams. Determine the magnitude of change in momentum during the bounce. So momentum, remember, is P equals mv. So this means that delta P equals mv minus mu, because u is the original velocity and v is the current velocity, if you know what I mean. So that means we can just get cracking. So 57 grams, so you don't actually put 57 here because in physics we use kilograms. So we actually use 57, 0.057. So I'll just write it over here to make things easier. So that's 0.057 times the velocity. So this is velocity after the bounce. So we're going to be using different numbers than ones we wrote here, because remember, this new line here is going to be the bounce. So the original velocity is minus 4.9 because it starts there, and as it's bouncing it accelerates up to 4, and there we go. Make sure to keep minus signs on calculations of momentum because they do come into effect. You need to pick a direction and make sure all your numbers are minus, got the correct sign, otherwise it just screws you over. So times 4 minus 0.057 times negative 4.9, and then we just shove this into our calculator. That's the beautiful thing about physics, is a lot of the questions you can just get away with plug-in number and just kind of monkey it. And there we go, we've got 0.5073. And again, you can actually just leave it like that. Make sure to put units in though. And this is momentum, so it's kilograms meters squared, and you can figure it out from a thing because it's mass and velocity, and you get mass velocity there. I'll round it to 2 decimal places. It's just what I like to do, but they will just accept their top answer there. So anyway, determine the magnitude of the average force exerted by the ball on the ground during the bounce. Now, how do we do this? Well, you see, remember, change in momentum, I'll represent that as delta P equals impulse, which in turn equals Ft. So you can say, well, Ft equals mv minus mu, which means that we already have time, but remember we're doing it in this section here. I'm sorry, there's quite a few lines going on now, so it's the time would actually be between 0.5 and 0.77, which means I'll go and just write off the side here. We'll have to get the difference rather to figure out the actual time, which is 0.27, and then we can start plugging the numbers. So force is the thing we're trying to work out, time is 0.27, and then we've already done this in this one here, so already calculated the change in momentum, so we can just plug that in, or whatever rounded you want. If you're keeping this in the calculator, you can probably just do it that way, and then divide like so. So you divide both sides by 0.27, so force will equal 0.51 divided by 0.27, and you get 1.8. So round it to 2 decimal places, probably it's a good idea, and make sure to put newtons as for force. And boom! Now we need to complete the sketch graph of acceleration A against time t for the ball between 0 seconds and 1.18 seconds after it's released. Numerical values are not required on the acceleration axis. Additional graph, if required, can be found on page 44 in case you flip up. So this one, numerical values are not required. That is a godsend, because then you don't actually need to do any calculations, and I would strongly recommend not putting them in, because in the marking scheme it does say if you do it, they have to be correct, and yeah, you don't really want to do that, eh? So what are we gonna do? How are we gonna figure this out? Well, we just need to kind of look at this graph here and try and look past all my weird scribbles to see what kind of acceleration. Because right, well, down here the gradient's negative, right? So acceleration must be negative, but up here it's positive. It's going upwards, so positive again, and then moving. But notice that the gradients of these two are both the same because they're both decelerating at the same rate because they're both going under gravity, right? So this is like the same force is being applied. But this one is much higher than them, even in the positive direction, say twice as high. So for that one, that means that down here, it will be at some value, say here, up and down, and then it hits the floor, and it's going to start accelerating back upwards. So it's going to jump all the way up here, and then as soon as it leaves the floor, there's no upward force acting on it, it's gravity just pulling it down, so it goes back down there. And then you sort it. So just make sure you get the extended bit during the period where the ball is actually bouncing up, not anywhere else. But there you go. Right, on to question 2. A student abseils down the outside of a building using a rope. Ooh, dangerous activity that. Mass of the student is 55 kilograms. Rope with negligible mass attached to a fixed point X to the top of the building. Rope makes an angle of 15 degrees to the building. So calculate weight of the student. This one, you don't need to, we won't need to worry about this 15 degrees rope bit at all. Because remember, gravity will pull you down no matter what weird rope setup you've got. It will always apply the same force when you're in the same mass, same bit in the gravitational field. So we're just going to go W equals mg. Mass is 55. Gravity, this is presumably on Earth. I have not been told about any buildings on Mars yet. So pull out our calculator. 5.9 times 0.8, 539. And there we go. Next up, determine the tension T in the rope. Right, so what's going to happen here is, because we're pulling down at 540 odd, roundabouts, 539, but down this way, but it's that's straight down. So what is going to be the tension on this angular bit here? So what we can do is remember our cosine and sine laws, because if you think, if I was dangling from a building, try and make sure try and make it look like I'm not hanging myself. Yeah, like I'm Spider-Man, right? I'm hanging from here, straight down, and I weigh 55 kilograms. There, then it's just gonna be 540 newtons of force going straight down. So that's if the angle was 0. But if I was going completely out here, and I was somehow, the rope wasn't bending or whatever, and I was living life out here, then there would be no tension in the rope, because it would have to swivel down. So if it's like a metal rod, there would be shear forces, but there wouldn't be tension, if you get what I mean. So what does this all mean? Well, it means that we can figure out which thing to use, because I'm going to be sine or cos. So if I plug 0 degrees into sine, we get 0. So that means that even if I was going completely downward, I wouldn't feel any weight. So that doesn't feel right. So it's probably not sine, let's face. But let's see if cos is definitely the right answer. So if I put 0 degrees into cos, I get 1. So I get the full Monty. But when I extend it out in the previous example, so I'll be at 90 degrees, and I did that with cos, it would get me 0, because there wouldn't be anything. So long-winded explanation. Basically, all you need to know is we're going to be using cos for this, right? So if we're going to be using cos, we can say, well, the tension in the rope is total force yeah, tension down is what we want. Tension weight is cos theta. Theta is the angle. This is what we have. This is what we want to get. So 540. Well, 39. We'll put 39 just to be really accurate. Hey, we don't know t, but we do know cos theta because that's 15 degrees. Fantastic. Then if we just do some basic rearranging, we can figure out t, original t. So we put 539 divided by 15 cos. What do we get? We get 558. And it's 0.0, so I'll just leave it as 558 newtons. As the student abseils down the building, the angle the rope makes for the building decreases. State whether the tension of the rope increases, decreases, or stays the same. Justify your answer. Right, so this is a justifying question, so you can just explain, but you can also recalculate it by using a smaller angle. I'll probably do that because I think it's a safer bet if you ask me. So let's pick a smaller angle, say 10 degrees. I'll just write smaller theta equals 10. And then we'll do the whole tension calculation again. Weight of the students remains the same. They don't like lose weight in the course of this. Ooh. Okay, cool. Then we'll do the same thing we did. 539 divided by cos of 10. 547. And put 0.3, I guess. So then you can just conclude 547.3 is less than 558. Therefore, tension decreases. And there we go. Right, we're moving on to question 3, and this is a doozy, I'm afraid. This is an open-ended question, and I would strongly recommend you leave open-ended questions to the very end of the paper because they take ages to do, and they're only worth 3 marks. Like, look, we did this in about 10 seconds, right? That's 3 marks. This takes 5 minutes to get 3 marks. It's an absolute nonsense. But yeah, so ideas for doing this. What it's getting at with a football tells teammates that a football can be kicked a much greater distance when the ball is initially travels towards them compared to kicking a stationary ball is conservation of momentum. I'll write off the finger space this time. I could use the text tool on this, but it's actually hot garbage, so I think I'll just stick with my terrible handwriting. But basically, idea is that total momentum before collision there's a lot of writing to these ones. Equals total momentum after collision, and I'll just shorten that out. You probably want to write the whole thing in your exam, but I can't be bothered. This means that M1 V1, that's V1, wouldn't it? And yeah, writing statements like this would actually get you quite far. If you write down formulas and like conservation of momentum, like laws of momentum and whatnot, that will help you bring up your physics to like, because the whole point of this question is you want to show the marker how well you know physics, how cool you are. So you want to write down as much equations to show that, yep, I've studied all this, right? But basically the idea is that, oh, okay, even used the bloody text tool. The greater the original, the speed of the ball before kicking, fix this out. The greater the initial momentum of the system, so the total momentum after collision is higher, so the ball moves at a high velocity, sorry. After the collision. That's okay. That's continuing to be good. That you can mention, because it's not just about having a faster ball, it's actually a greater distance. So you can start talking about, be like, okay, higher horizontal velocity, because we're kicking it horizontal. Horizontal velocity, if I could actually spell, means more time in the air before it hits ground, in other words, so it travels further. A higher vertical velocity. And a higher horizontal velocity. Means for every second in the air, the ball travels further. So yeah, that's a good start. I recommend at the end of the paper you just start rambling on these, just mentioning any old thing, because I don't think you can get points of writing too much down, unlike in biology and garbage subjects like that. But yeah, that's the general premise. But you can also go into like physics of bouncing. So like when you hit a ball, it like squeezes and then expands back out. Show that. So we can say energy is lost during that. You can say it will be harder to hit. Harder to hit when it's moving towards you, because you wouldn't be able to. It's, you know, you've got a shorter window. It's harder to aim, and so on and so forth. So there's a lot of things you can talk about there, but yeah, I think this is at least a good start. Probably get you at least 1 or 2 marks. But you really do, for these ones, you really do just have to ramble, unfortunately. It's just kind of the nature of the game. I usually fill up both these pages with utter nonsense. Righty, we're on to 4. Communication satellite operates at a height of 36.0 times 6 meters above the surface of the Earth. Remember, it's the surface of the Earth, not the center, from the center, which is what we'll need later. Hint, hint. And then the mass of the Earth is 6 times 10 to the 24 kilograms, so the radius of the Earth is 6.4 times 6 meters. In terms of distancing the center of the Earth from a satellite, it's one marker, so it should be solid. So basically, if you've seen from my beautiful diagram over here, oh, isn't just splendid? We need to add these two numbers together, because if I overlay this on here, we want to find out the distance between it and the center. and radius of the Earth is 6.4 times 10 to the 6. So we need to add these two numbers together. So let's quickly do that. Beautiful, and hop to our calculator. .24 times 10 to the 7. And it's in meters. That's perfect. Gravitational field strength, the force of attraction, I mean, is between the Earth and the Sun is 57 newtons. Fantastic. Okay, so what we're going to have to do for this one is go over here and remember this equation. So F equals G, which is the universal constant of gravitation, times M1 times M2 divided by R squared. Okay, so let's write that down. That is a 6. So yeah, there you go. We know G because it's a constant, it's in your data booklet somewhere. We know force because it tells us it. We know one of the masses because it tells us the mass of the Earth, and we know the distance between them because we just worked it out. So we don't know the mass. We need to rearrange this formula to get one of the masses. So let's go and start doing that. I'll do it step by step. F over G equals M1 M2 of R squared. So that means R squared times F over G equals M1 M2, and then we divide both sides probably by M2 to get R squared times F over G divided by M2. A bit messy, I know, but we're just going to shove this in our calculator and leave. So that means if we throw in our numbers, because the radius is, I'll put it in brackets, 4.24 times 10 to the 7 squared times, so force is 57, and gravitational constant is some hilarious number. It is 6.67 times 10 to the minus 11. I'll just double check that. It's either minus 11 or minus 18. I cannot remember. But it doesn't matter because I'll show you right where it is. There it is right there in all its glory. 6.67 times 10 to the minus 11. I was right. Oh, that feels good. But yeah, here we are. And then divide all of that nonsense by M2, which is the mass of the Earth, which is 6 times 10 to the 24. So yeah, and then this all equals mass. So mass is what? Well, start by squaring that, and then we times it by 57 divided by 6.67 to 11. That gives us this horrific number, and then we divide by 6 times 10 to the 24. And we have 256. Kilograms. Right. Splendid. Let's continue on forth. I'll leave this calculator up, I think. Determine the value of the Earth's gravitational field strength G at the satellite. So 2 ways you can go about doing this. You could actually just do this formula again, but you replace one of the m's with 1. Yeah, that you can do that. It's probably a bit wasteful because you have to deal with this all constant one, and it's just a bit pain. So, but also, our old friend W equals mg, you can just use him. Because, well, we know that the weight is 57, and we know that the mass is 256 or whatever. So we can use that to figure out G. So we divide 57 by 256, we should get G. That's not. I forgot you have to put a 2 in front of the 256. Okay, and it's 0.22. And put it as newtons per kilogram. A second satellite has a quarter of the mass of the first satellite. The distance from the centre of the Earth to the second satellite is half the distance from the centre of the Earth due to the first satellite. State how the gravitational force of attraction between the second satellite and the Earth compares with to the gravitational force of attraction between the first satellite and the Earth. Right. So for this one, I would recommend probably doing it by calculation, because it's just I prefer it, but essentially the answer we'll get is that they'll both be the same, because if you have remember it's m over r squared, so you have a quarter of the mass, that'll be 0.25 for your mass, and then that means that compared to the original, and then the radius is half the distance, but if you square a half you get 0.25, so you'd end up with the same force. But let's justify it by calculation just in case. So 256 divided by 4 is 64, but I'll just triple check, I'm very paranoid. And then it's half the distance from the centre of the Earth, so it's 4.24 times 10 to the 7 divided by 2. And that's 2.12 times 10 to the 7. Excuse me. And then we'll just shove it into the equation again. Gravitational field strength is 6.67 times 10 to the negative 11. Constant, I mean, sorry. And then mass of the Earth will stay the same. There we go. And then we just shove this all in our calculator. Oh, I need to use brackets. Yep, we get this number, and then divide by the gravitational constant. Ignore the fact that I just divided by the gravitational constant instead of, multiplying by it. Right, try that again. And there we go, we'll put it out of scientific form. And oh, look at that, it's 57 newtons. So then you can say force is exactly the same. A person is standing on the side of the road, like many people do. A car travels along the road towards the person at a constant speed of 12 meters per second. The car emits a sound of frequency 510 hertz from their K-pop or whatever. The person observes that the frequency of the sound changes as the car passes. State a name given to the effect. Well, it's everyone's favourite Doppler effect, and I can't really explain that. That's just what it's called. You're going to have to remember that. Dopplers when frequency changes when objects are moving. Alright, and we move on to the second part of question 5. Calculate the frequency of the sound heard by the person as the car approaches, blasting its K-pop. Right, well, we want to use our relationships here. F0 equals Fs with V over V plus or minus Vs. So V is the speed of sound in air, or like, you know, whatever the frequency medium travel in, and Vs is the movement of the source. So I'm going to write that in. Undo that by accident. And are we going to plus or minus? Well, we're going to minus it because when you're doing it, it's the like kind of the opposite of what you think. You just think if it's coming towards you, it's plus. If it's going away from you, it'll be minus. But it's the opposite way around. If it's coming, the source is coming towards you, it's minus. But if it's going away from you, it's plus. But anyway, let's go and 510. This is the frequency of the source. 340. That's the speed of sound in there. 340 minus 12 brackets. Let's solve that. Alright, and then we times that by the frequency. We get a slightly higher number, 528.7 Hertz. And there you go. You might want to round that up a wee bit, maybe to 529 Hertz or something. SQA can be quite finicky with their significant figures, but 528.7 Hertz works out perfectly fine. Moving on to B. The same effect is used to determine the speed of red blood cells through blood vessels. So you've got this probe that's bouncing sounds off red blood cells, and then theta is the direction. Theta is the angle of the probe compared to the direction of the blood go, and so forth. So ultraviolet wave transmitted flow. The frequency of the ultraviolet waves change as they reflect from the blood cells. The probe detects the reflected waves. The velocity of the red blood cells can be determined using the following relationship, and it's this horrific equation. I'm sorry about what's about to unfold. So, F lambda is the change of frequency. F is the transmitted frequency, so what the probe is outputting in originally. VRBC is the velocity of the red blood cells. V is the velocity of the ultrasound. Theta is the angle between the direction of the waves and the direction of the blood flow. The frequency of the ultrasound transmitted by the probe is 3.7 megahertz, because why not? So what I'll do is I'm going to I'll write this in. The transmitted frequency is 3.7 times 10 to the 6. The velocity of the ultrasound was 1,540 meters per second, so I'll write it in there. During one test, the angle between the direction of the waves and blood flow was 60 degrees. The change in frequency of the ultrasound is 286 Hertz. Okay, so I'm going to write that in. And it's 60 degrees here. So we've got everything apart from the velocity of the blood cells, which we want. So the main difficulty in this equation is we just have to refactor it, essentially. So I'm going to start by multiplying both sides by V. So delta F V equals 2F. I'll just shorten it to VR. I'm not having VRBC around here, mate. What on earth? Cos theta. And I'll leave the numbers out for now. Okay, so then all we need to do from here is just divide both sides by 2F cos theta. So equals VRBC or whatever. So then let's go and throw all the bloody numbers into it. So that's 286. It's just 286 Hertz, ain't it? Yep. And then times by the transmitted, times by the velocity of the ultrasound, which is 1,540, over 2 times the original, which is the transmitted frequency, which is 3 times 7 times 10 to the power of 6 times cos 60 degrees. Easy one. I'm terrified of this. And then we just need to throw that into our calculator and get the R. So, bracket 286 times 1540 divided by another bracket 2 times 3.7 to the 6 times 60 cos bracket. Oh, and then we get this number. 0. I'm going to round it to 2 decimal places. But yeah, we'll keep it at 2 decimal places. You can't stop me, SQA. And there we go. Oh, long one, ain't it? Right, we're moving on to 6 now. The graph, stars emit radiation with a range of wavelengths. The peak wavelength of the radiation depends on the surface temperature of the star. The graph shows how the energy emitted per second unit area varies with the wavelength lambda of the radiation for a star with a surface temperature of 5000 Kelvin. Okay. A second star has a surface temperature of 6000 Kelvin. On the graph above, add a line to show how the energy emitted per second of unit area varies with the wavelength lambda of the radiation of the second star. Sorry, just a bit tired. So, well, I mean, all you really need to do for this one is use some common sense, right? It's hotter. It's going to produce more infrared. It's going to have more stuff coming off it. So it's just going to be, it's going to be higher for one, but is it going to maintain the same shape? Well, it should do, right? Because it's it doesn't say there's any differences between the stars materially, so it should be outputting the same wavelengths, but just make sure that the line is always above the original thing. Because it's hotter though, this means that it'll be outputting higher energy waves. Now higher energy waves have smaller wavelengths, which means the peak won't be exactly in line. It should be like over here somewhere. So it's always going to be hotter. That means that peak will be like there, and then it will slowly go down. Right? You just need to make sure the peak is before of the second star is before this peak, and it's always hotter. It's always got more radiance. Okay, there we go. 6b. The table gives the surface temperature T in Kelvin of 4 different stars and the peak wavelength of radiation emitted from each star. Use all the data in the table to show that the relationship between the surface temperature T of a star and the peak wavelength lambda peak radiated from star is this. Right. I'm sorry. I absolutely despise these questions. They're just really, really irritating. They're just super repetitive. But first thing I want to do is I'm wanting to make this appears to be a constant, right? 2.9 times 10 to the minus 3. So if we can make it as the constant equals something, and then we can just run that calculation a billion times. So let's go and rearrange this. So that means T lambda peak equals 2.9 times 10 to the negative 3. Okay, that's cool. So then let's just run through all these. And I'm afraid you literally just have to write this. I don't know why they do this. Like, the SQA is just evil. Seven, 6 times 10 to the minus 7. And I wonder what happens when you multiply them together. No way you would get the thing that we were looking for. Yeah, I'm just not a big fan of these kind of questions, you can tell. Oh, wow! It equals 2.9 times 10 to the negative 3. Who could have seen this coming? And you better believe it, folks. We're just going to do it again 3 more times. I'm going to make you suffer with me, mate. You're going down with me. I'm sorry. One day I'll get rid of these, and then the world will be a happy place. Yeah, hopefully in editing I'll speed this up, maybe, but... And we're back. So, once we've done this horrific mess, we just need to say, therefore, t times lambda peak equals a constant, i.e. what we've been calculating this whole time, of 2.9 times 10 to the minus 3. Yeah, that was really fun. But hey, new question, new life, eh? So, number 7. Scientists have recently discovered a type of particle called a pentaquark. Whoa! Pentaquarks are very short-lived and contain 5 quarks, as the name should suggest. A lambda B pentaquark contains the following quarks: 2 up, 1 down, 1 charm, and 1 anti-charm quark. Quarks and leptons are fundamental particles. So what is a fundamental particle? Well, fundamental particles are the building blocks of the universe, like a Lego brick, right? When you're building a Lego model, you use many Lego bricks, but you don't get a hammer and split Lego pieces down the center. You know, you can't break them into bits. They're not composed of small Lego bricks, right? So you can just write down one of these. So you can say fundamental particles cannot be broken down into smaller particles, or you can say they're not composed of smaller particles. And there we go. State the name given to the group of matter particles that contains quarks and leptons. So again, this is just going to be one of those, you need to remember these, but they're called fermions. Yeah. That's it. Matter particles are called fermions. Remember that. I'm afraid there's not much more than that. But anyway, the table contains information about the charge on the quarks that make up the lambda B pentaquark. Cool. So determine the total charge on the lambda B pentaquark. Well, it tells us the charge right here, guys. And it tells us what it's made out of. So I think we can probably do this. So it's got 2 up quarks. So that means it's 2 over 3. And it's also got 1 down. So we can add minus a third. And it's also made out of a charm and an anti-charm. So those will actually cancel each other out. So you can actually... that might make the maths easier if you were not doing this without a calculator. But I'll go the whole Monty for you folks. Don't say I'm not good to you. What did I do? About 3, and then plus brackets 1 divided by 3. Plus 2 divided by 3. minus 2 divided by 3. What do we get? We get 1. And yeah, you probably want to use E because that's the charge we've been using. And it's positive 1, so probably best to actually put a positive sign next to it. But yeah, that's it. Anyway, moving on. One theory to explain the structure of the lambda B pentaquark suggests 3 of the quarks grouped together and 1 quark in the antiquark grouped together within the pentaquark. State the type of particle that is made of a quark-antiquark pair. And again, a lot of this particle physics stuff, you just have to remember it. Quark-antiquark pair is called a meson. The mean lifetime of another quark-antiquark pair is 8.0 times 10 to the negative 21 seconds in its own frame of reference. During an experiment, the quark-antiquark pair is travelling with a velocity of 0.19 c, c being the speed of light, relative to a stationary observer. Calculate the mean lifetime of this quark-antiquark pair relative to the stationary observer. So, this is where it actually gets interesting. We can use relativity, which is right here. So T1, T prime is the altered one, and T is what it's for the original observer. So let's just shove it in. T prime equals T over root 1 minus V over C squared. Fantastic. And this V over C term, we can just replace that with 0.19c, because that's really what it means. So yeah, let's just plug in the numbers. 8 times 10 to the negative 21 over root 1 minus 0.91 squared, and we should just be getting an answer. So I have to do this whole rigmarole. There we go. We figured out that its answer is 1.93 times 10 to the minus 20 seconds. And we're sorted. Right, moving on. Lambda B pentaquark has a mass energy equivalent of 4,450 mega electron volts. Where 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Determine the energy in joules of the lambda B pentaquark. Okay, well this is simple. If 1 EV is equal to 1.6 times 10 to the minus 19, then that's simply 450 times 1.6, and then I'll put this in brackets, 19. But since it's mega electron volts, it's actually 10 to the 6. And then this will give us our total energy. So yeah, just find this into our calculator. Gives us 7.12 times 10 to the negative 10, which doesn't seem like a lot, but that's one particle using all that energy. Well, one particle, I assume, producing all energy. So it's actually quite a fair chunk of change. So go and write that down. Remember, units of energy is joules. Calculate the mass of the lambda B pentaquark. Okay, well, let's go and do it. So what we're going to have to do here is, I don't think you need to go into the relationship with this one. Everyone remembers E equals mc squared, right? So we know the energy. So that's 7.12 times 10 to the 10. Minus 10, sorry. Remember your minuses, guys. Equals m. That's what we want to figure out. And c is a constant. It's the speed of light. E equals m squared is such a good equation. There's so little to do on it. So yeah, I'm just going to divide this by the square of the speed of light, and then we'll get the mass. So divide that by brackets 3 and 10, and then square it. That will give us this number, and that's our answer. 7.91 times 10 to the negative 27 kilograms. So yeah, quite light. And there we go. The sun emits energy at an average rate of 4.1 times 10 to the 26 joules per second. This energy is produced by nuclear reactions taking place inside the sun. The following statement shows one reaction that takes place inside the sun. State the name given to this type of nuclear reaction. Well, let's have a look at this, right? Well, for one, it's using quite light nuclei, so it's unlikely going to be fission, right? But also, it's combining them together, as you can see. Look, you have two hydrogens, and then you slap them together to get a helium-3 and a neutron. What on earth? So that's got to be fusion. So I'm going to say nuclear fusion. You can just get away with saying fusion, but we'll be proper about this. Make sure to spell fusion correctly, because they get fussy, because they say you can confuse it with fission or something, so be careful. Remember, it's F-U-S-I-O-N. Okay? And I get your mark. And now, 4 mark, here we go. The mass of the particles involved in this reaction are shown in the table. So yeah, it's right there. And determine the energy released in the reaction. So, what you have to do here is you have to do a ton of boxes, essentially. So, mass before. So this is before the reaction takes place. I'm sure you guys can read that right. So, before the reaction, it's just these two hydrogen atoms, right? So, we're going to have 2 of these. And they've got a huge amount of significant figures, so I'll write them all down, but oh dear. Right, and then mass after equals is a helium particle and a neutron, so I'm going to write that down. Alright, and we'll actually run the numbers for this. This one, size is going to be a bit dry, but that's sometimes how it goes. Right, 0.6.68 31 times 10 to the negative 27. Fantastic. Right. So then what we can do is figure out the mass loss between them. So if we take away 6.6872 times 10 to the 27 minus 27 away, oh, here we go. Alright, put up the old history function on this. Yeah, it's really worthwhile keeping these in your calculator. Hit that button and we end up with mass loss equals 4.1 times 10 to the negative 30 kilograms. And would you believe it or not, folks, that is the first mark of the question. I know, all that was the first mark, so I'm going to have to do some scheming, but basically what you do from here is you do the rest of it. You've got your mass, you go and write down E equals mc squared, You don't know the energy because that's we want the energy. So the mass lost, because the mass loss would have to be turned into energy. And then times by the speed of light. Yeah, that's going to get weird, isn't it? So then if we run that through, we get our final answer. (3.69 times 10 to the minus 13 joules. Whew. Wasn't that a roller coaster? Oh man, right. Number C. Determine the number of these reactions that would be required per second to produce the sun's average energy output. Okay. Well, luckily it tells us the sun emits energy at an average rate of 4.1 times 10 to the 26 joules per second. So all we need to do here is divide that huge number by this really small number to get a really, really big number. Because it's joules per second, so if we divide it by, this is amount of energy one reaction would produce, so divided by the number of joules per second, we'll end up with how many reactions are needed per second. So, if we go and do that, geez, shouldn't have picked physics. I'm just terrified of all the bloody huge numbers. Boom. Monstrous number. 1.1 times 10 to the 39 reactions per second. Oh, and we're on to question 9. A laser emit lights when electrons are stimulated to fall from a high energy level to a lower energy level. The diagram shows some of the energy levels involved. In one particular laser, a photon is produced by the electrons transition from E5 to E3 as shown. It goes from that to that. Determine the wavelength of the photon emitted. So, how are we going to solve this? Well, firstly, we're going to calculate the energy of the photon. We can do that by calculating the difference between these two numbers. Okay, then secondly, we can use that energy to calculate the frequency of the photon. Oh, cool. And then we can use that frequency to calculate the wavelength. And we've answered the question. So let's get cracking then, eh? So I'm going to take these numbers away from each other. I'm not going to bother with the scientific notation because they're the same power of 10. So I can take them away all I want. And it makes the calculations a bit simpler. And we get 0.314. So then that would be multiplied by 10 to the minus 18. Okay. Right, then we need to use E equals HF. H is Planck's constant. It's, well, constant, so it's always going to be 6.63 times 10 to the negative 34. E is what we just calculated. And then F is what we want to get. So to get F, we're going to divide what we've just calculated by Planck's constant. So 0.134 to 18. That's not what I wanted. 0.134 to the power of 18. There we go. Then divide that by 6.63 times to the 10 to the minus 34. We get this huge number, which is our frequency. Yeah, you can go endless with this, but well. Right, now we've got frequency. What we need to do is put it into this equation. V equals F lambda It's the speed of light, so it's going to be 3 times 10 to the 8. Frequency is what we just calculated, 4.736 times 10 to the 14. And then lambda is what we want to get. So if we just get this and divide it by the speed of light, so if I copy 3 times, so this is the speed of light, and there we go. That's not what I wanted to do. So 3 times 10 light, fantastic. Divide it by that, what do we get? Oh, we get this number, which is our wavelength. There we go, that's 4 marks. The laser beam is then shone onto a screen. The beam produces a spot of diameter 8 times 10 to the negative 4 meters. The radius of the spot of light on the screen is 9,950 watts per square meter. Determine the power of the laser beam. Okay, well for this one, we're going to think back and figure out what an area of the circle is. So remember, area of the circle is pi r squared. But this is the diameter, not the radius. So radius would equal 8 times 8.0 times 10 to the negative 4 divided by 2, which is obviously 4 times 10 to the negative 4 meters. That's supposed to be 4, not a 9. There we go. So then we just plug that into here. So pi times brackets 4 times 10 to the power of negative 4, then all that squared, and then we can shove it in our calculator. So pi times brackets 4 small brackets squared. Well, we get this. 5.03 times 10 to the negative 7 meters squared. And then what we need to do now is think radius is power over area. So that means if the radius is 9,950, power and area is over this. Then power has to be that this times that, i.e. about 5 milliwatts. Boom. Okay. B. A student investigates how the irradiance I varies with distance d from the point source of light using the apparatus as shown. So we got a small lab bench covered in black cloth, a light sensor, a light meter, a meter stick. Described as an apparatus could be used to verify the inverse square law for a point source of light. So inverse square law works quite well on graph paper when you graph it out, because it will look something along the lines of this. Right, further you get away, the radiance will go down and down. But an even better way to show it is if you plot it against 1 over d squared, because that will cancel out weirdness, and you'll have a perfectly straight line. So what you want to do is get value, so obtain if you want to be smart. Use of the irradiance for different distances. So you're going to be measuring from different distances on this meter stick. Then you're going to plot a graph of I, against, I am just reading this off the marking scheme, by the way, but this is roughly what you should be doing, against 1 over d squared, and then graph, that's the final mark, graph of I against one over d is a straight line and goes for the origin. Yeah, so whenever you want to confirm a relationship or something like this, getting a graph that goes directly for the origin is what you want. Wow, I'm great at spelling, aren't I? Yeah, so that's basically verbatim from the marking scheme, honestly. But this will work for everyone's. You want to get, if it asks, how could this be used to verify in the square one? Just make sure you get a graph that the thing goes through the origin, and then you can work it out from there. Right, everyone, we're going to be doing question 10. So, yeah. Student carries out an experiment to investigate this effect of grating on the beams of light from 3 different lasers. The 3 different lasers produce red, green, and blue light respectively. Each laser beam is directed in turn towards the grating. The grating has a slit celebration of 3.3 times 10 to the minus 6. So yeah, let's get cracking with this. State in which the 3 colors laser light produce a small angle theta between the central maximum and the first order maximum. So I usually do this by calculation, but if you did by calculation, you have to calculate for 3 colors of light, and that that's kind of boring. So let's just look at the equation, right? And you can do it just to double check, but let's try and do it wordy this time, maybe just to switch things up, right? So we're looking at this, right? Sine is proportional to, if you want a small angle, you want sine of that angle to be small, because it's the theta and sine theta are going to be both increasing in the first quadrant, which is what we're looking at. D is going to stay the same. So the only way to decrease the angle is have the smallest wavelength possible. And the smallest wavelength of these 3 lasers is blue light, right? Because you have Roy G. Biv. And over this one is decreasing wavelength. Right? So that means that blue is in this set, blue is the lowest wavelength. So you want to be using blue light. So we know that, but how are we going to describe it? So you can say sine no h is proportional to lambda, because m and d both stay the same. And then you can say that blue light has the shortest wavelength. And there you go, pretty much. I'm going to say compared to red and green, just to make it clear what we're on about. But otherwise, we should be fine. There we go. Right, now we actually get to do some proper calculations. The angle theta between the central maximum and the first order maximum from light from one of the lasers is 8.9 degrees. Calculate the wavelength of this light. Well, that equation we're going to use, we just put up there. Let's go and reuse it, eh? Cool. Right, we know the slit separation. That's 3.3 times 10 to the negative 6. Times sine 8.9. angle between the central maximum and first order maximum, so that would just be 1. So now we can just run this through. 3.3 times 10 to the negative 6 multiplied by 8.9 sine equals wavelength must then equal 5.1. I'll put it round to 5.11 times 10 to the negative 7 meters. Determine the colour of the light from a laser. Okay, well, might have no idea how to do this. A lot of people out here like stumble into this, but what you do is go all the way up to the data sheet, and then it was 510 nanometers roughly, because it's 1 nanometer is 10 to the 9. So if it's 10 to 7, it's 100 nanometers, so 500 nanometers, right? That means we can have a look at this and see if there's anything very similar. And, 510 nanometers, you say? That's very similar to this one that just says 509 is green. So I think we can write down green. Jeez, I really do make these papers really bloody long, don't they? So yeah, you can literally just write green, and there's your answer. Another student suggests that a more accurate value from the wavelength of the laser light can be found if a grating with a slit separation of 5 times 10 to the negative 6 meters is used. Right, well, explain why this suggestion is correct, so we can go and murder this other student. So, again, what we can do is write down our equation that we've been using. So then we can say that if we're getting this angle right, so that means that, yes, remember this is we want to be separated input and output, right? So we said that if we increase D, which is supposed to be that, then we'll get a higher value, but we'll actually get a lower value. So we say if D increases, then will be smaller. So harder to measure, so greater uncertainty. You got to make sure to say percentage uncertainty for some reason. Because it has to be a specific type of uncertainty. It's because it's not reading uncertainty or systematic uncertainty. Right. Number 11. Diamonds sparkle. Whoa! Because light that enters the diamond is reflected back to the observer. A ray of monochromatic light is incident on the diamond at an angle of 49 degrees. The refractive index of the diamond's furthest light is 2.42. Calculate the angle of refraction theta. Well, what we do here is we have n equals sine theta air over sine theta glass, or actually it's not glass, it's diamond, so might want to label that correctly. So sine theta glass, air is 49. 2.42 over here. So sine theta diamond is what we're looking for. So we just need to swap these two numbers around essentially, and then we can just go 49 sine divided by 2.42. We get this number, which equal sign diamond, so but we want the angle. So I'm going to go and reverse sign that. Hold the phone, folks. It wouldn't be a classic. It wouldn't be a paper going over without me flipping something up majorly. Right, so we have this number. I'm going to go and inverse sign it. And there we go. It would be 18.17 degrees. Right. Calculate the critical angle for the diamond as light. What's the critical angle? That's when it starts reflecting internally instead of refracting. Critical angle here is this. Sine equals 1 over n. So that means sine over c equals 1 over 2.42. So lambda, theta c equals, so obviously 1 divided by 2.42. But then we need to inverse sine, because this is what sine theta is equal to, but we want just theta. There we go. So it'll be 24.4 degrees. Moissanite is a transparent material of a greater refractive index with diamond. A sample of moissanite is made of the same shape as the diamond. State whether the sample of moissanite sparkles more or less than diamond. You must justify your answer. So for this one, I think I'm going to do it by calculation. So we'll say moissanite refractive index is 3 or something. So we can go sine equals 1 over n. It's 1 over 3. So the critical angle is what? (19.47 degrees). So you can say 2.4 is greater than 19.47. So you can get the critical angle smaller in moissanite than in diamond. So internal reflections are more likely with moissanite, so more sparkle. Whew, there we go. Moving on to 12A, a student sets up a circuit shown. When the switch S is open, the reading on the voltmeter is 1.5 volts. Switch S is now closed. The reading on the voltmeter is now 1.3 volts, and the reading on the ammeter is 0.88 amps. State the EMF E of the cell. Well, you can measure the EMF by connecting a voltmeter to the terminals of the battery of the cell when there's no charge going through it, and when S is open, there's no charge going through it. So that means we can use this thing here, and it will just be 1.5 volts. Right, moving on to calculate the internal resistance R of the cell. What we can do is use this relationship here, equals V plus IR. So V is the current voltage, and then IR, that's the current, and that's the internal resistance. So 1.5 equals 1.3 plus 0.88 times R. So that if we take away 1.3 from both sides, that's 0.2 equals 0.88 times R. So if we divide both sides by 0.88, we should get R. So 0.2 divided by 0.88, we get this number, which is our internal resistance. Explain why the reading on the voltmeter decreases when the switch is closed. Because closing the switch allows current to pass through the circuit. Current to flow, I should say. Let's see if we can spell circuit correctly. Probably not. So that means that voltage is lost across the internal resistance. Because resistance doesn't do anything unless there's current going through a circuit that it can resist, Otherwise, just sits there doing flip all. Right, and now on to 12B. A battery of EMF 9 volts and alternative resistance 1.2 ohms is connected in series with a lamp. The lamp has resistance of 2.4 ohms. Can determine the current to the lamp. So let's have a look in our relationship sheet, see if we can spot anything useful, and have a look around. Or do they? I don't know if they actually write this one in. Oh no, they don't. Wow, that's a bummer. Well, don't worry, because you can use E equals I R plus R, and that's because we get it from E equals V plus IR, but V equals IR in itself. So, and then you can divide both sides by I. Right. So we know the electromotive force. We don't know I, but we do know both resistances. I'm just going to put the wrong way around for some reason. Don't know why I did that. Just I'm a menace to society. So then I will be 9 divided by what 1.2 plus 2.4 is, which is 2.5. Calculate the power dissipated in the lamp. Well, there's plenty of power equations to go around, but I know we have resistance and we have current, so I'm going to use P equals I squared R. I squared is 2.5 times R, which is 2.4. Let's see what we get. We get 15 watts exactly. A student investigates the charging of a capacitor. The student sets up the circuit as shown using a 47 micro-ohm capacitor. The capacitor is initially uncharged. The switch S is now closed. A laptop connected to an interface displays a graph of current against time as the capacitor charges. The variable voltage supply is set at 6 volts. Calculate the maximum charge stored by the capacitor. Well, let's hop into a relationship sheet, and oh, here we go. C equals Q over V. Let's try and write that. So Q is charge. So that's what we want to figure out. But we know capacitance. and voltage is 6. So we just times capacitance by 6 and we'll get the amount of charge. And there we go. We've got 2.82 times 10 to the negative 4 coulombs. The graph shows how the current I varies with time t as the capacitor charges. Switch S is opened and the capacitor is discharged. The resistor is now replaced with one that has greater resistance. Switch S is then again closed and the capacitor charges. Outline the graph to show how the current now varies with time as the capacitor charges. Well, what this means is, remember, more resistance means less current. So that means it will have a lower starting current, let's say here. But what about the rest of the curve? Would it follow the original thing? Well, no, because less current means there's less charge getting into the capacitor per second, which means it takes way longer to charge, so it takes a longer time. So you have a nice gentle curve down there. Okay, number C. Suggest an alteration the student can make to the circuit to increase the maximum energy stored by the 47 microfarad capacitor. Well, there's only one way, completely, because if we look at our physics relationship sheet, it's mentioning the same capacitor, so we can't change capacitance. The only way is to increase voltage. So we can just say increase the supply voltage, or increase voltage supplied to the capacitor. Oops. Can't even draw an E. 13D. Oh no, it's another open-ended question. No. The use of analogies from everyday life can help improve the understanding of physics concepts. Vehicles using a car park may be taken as an analogy for the charging of a capacitor. Use your analogy fix to comment on an analogy. Right, so we want to say the good and the bad, but let's start with the dead obvious. Cars equal electrons. Yeah, so the cars represent electrons going into capacitor, they get stored, and then when they discharge, they get thrown out, right? So then we can start saying things that are good about the model. You can say capacitor has fixed capacity. Like car park. There's limited number of spots. So there's only so much charge you can hold in a capacitor, right? You can increase that by increasing the number of voltage, which is kind of a flaw in this analogy, though. So you could say voltage is the energy in the cars. You could even say the speed bump is internal resistance. Now let's start a thing that's not so good. You can say I'm actually gonna, so capacitor has a fixed capacity as a unfixed capacitor because you can store more charge in it than. Sorry, I got that wrong first time, but you can store more charge in a capacitor if you increase the voltage. So you can say unlike a car park. You can also say motorbikes and cars of different masses, while all electrons have the same mass. Say, okay, then a good point we could say one way. Oh, that's not cut. Yeah, that's kind of a bad. So I had an idea and it was kind of bad. So you can say that you get it's easy at the start to put stuff in, but it builds up resistance because it's easy to find like a parking spot where there's loads around, but as it gets filled up, it gets harder and harder. So you can write that down. You can say as capacitor charges, rate of charge decreases. Car park. That's a car park fills up. I mean, harder to find the spot. So reduces rate of filling up. And you can figure out 5 million other different ways. You can say I always one that I always write down just because it's kind of funny. Is you can say car park is much bigger than capacitor because it's obviously stupid, but it's technically right. It's more for universe stuff than but yeah, it just helps you get extended scale. And it would say electrons are much smaller than cars. Yeah, I might give the marker a chuckle, and that's always a help. There we go. And let's move on. You can ramble about this for ages, but I'm just writing down kind of the basics. So, 14. Solids can be categorized to conductors, insulators, or semiconductors depending on their ability to conduct electricity. The diagrams of the electrical conductivity can be explained using band theory. The diagrams show the valence conduction bands of three solids, X, Y, and Z. One represents a conductor, one represents an insulator, and one represents a semiconductor. Complete the table to show which solid represents a conductor and its insulator is a semiconductor. So conductor, important thing to know, is that the valence band overlaps with conduction band. So meaning that it's always able to conduct at room temperature. You don't need to excite the electrons at all. And well, would you look at that, solid Z, that looks like a conductor to me. Because you can perfectly see it's overlapping. Next up, we'll go with semiconductor first. Semiconductor has a band gap, but it's quite small, so you can get electrons to jump over if you excite them enough. But it's not overlapping like conductor. Solid Y, it's small, but it's not as big as solid X, so I'm going to put it in a semiconductor. Jeez, what is that handwriting? There we go. And then, well, you can use process of elimination to figure out what solid X is. But yeah, massive band gap, so it's got to be an insulator. electrons won't ever pass through unless you put ludicrous amounts of voltage in it. Righty. 14b. Using band theory, explain why conduction can take place in a semiconductor at a room temperature. Well, it's because band gap is small. So some electrons, not all, a few. That's energy, not electrons. Enough energy to cross the band gap. The valence and conduction bands. There we go. Silicon can be doped with arsenic to produce an N-type semiconductor. State the effect that doping has on the conductivity of silicon. Well, it increases it because this adds more electrons, unpaired electrons into it, and are free to move around, increasing the conductivity. It's like adding more ions to water. If you add salt to water, increases in conductivity. It's the same thing here. You're adding more free-moving ions. Resistivity is a measure of the material's property to oppose the flow of charge. The resistivity of silicon is 2.3 times 10 to the 3 ohms per meter. Resistivity of copper is 1.7 times 10 to the minus 8 ohms per meter. Compare the resistivity of silicon to the resistivity of copper in terms of order of magnitude. So then what we're going to do is we're just going to, when it tells you to do this, you just divide the numbers by each other. And we're going to get some sort of answer. We've just got 1.35 times 10 to the 11. So that means that resistivity of silicon is 11 orders of magnitude greater than copper. Oh dear, that was just reading my handwriting there. There we go. Right, we're on to the last question, folks. It's on 15. A 1 meter long wooden rod has a series of small holes drilled at 10mm intervals along its length. The rod is hung on a horizontal pin passing through a hole 50mm from one end. The rod is then raised for a small angle and released. The period T is the time for the rod to travel from A to B and back to A. Describe a method to obtain an accurate value for the period T using only a stopwatch. So what you want to do is, this is in magic physics lands, it's not going to deteriorate in its real life pending will get slow, get smaller and smaller. But since it's a physics land, it's just going to keep going back and forward. So are we going to get an accurate value for the period T? Well, if we set it going and leave it there, we can then count the number of swings and then divide, count the number of swings and then take the time and then divide by the number of swings. So we can say measure time over multiple swings. And divide by number. Oh, this handwriting is getting worse and worse. Of swings. There we go. The rod is hung from different holes in turn, and the distance h from the pin to the midpoint of the rod is recorded. T is determined for each value of h. The results are shown in the table. Using the square ruled paper on page 41, draw a graph of T against h. So you know what that means, folks. I'm going to have to go and draw this all out. Oh well. Right. Yeah, so this will be a bit difficult to show on the computer, but oh well, we'll get it sorted, don't you worry. Right, so if I scroll all the way, yeah, this is just so I can be lazy and have two tabs open at the same time. We'll get rid of our calculator for now. So yeah, this is going to be a bit boring, I'm afraid. But so it's T against H. We want T on this side, and we want H on this side. So H in terms of meters. Let's have a look at that. Let's try and be sensible. So I'm thinking we can just go straight. Every 100th of a meter is one division. So let's try that. And yeah, that would work, but it might not take up the entirety of the graph, so I'm going to double it. So I have this as 0.05, 0.11, 0.15, 0.2, 0.25, 0.3, 0. Cut. Right, so I've got a graph prepared, T against H. I've not made it easy, unfortunately, in SQA. Why would they make anything easy? No, it's always a complete mess every single time. But oh well. Okay. So H is on this side, so I'm going to go and start. I'm just going to write down the values here. So I'm going to just go one division. So that'll be 1.1. That'll be 1.0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So this is H in meters. And then remember to draw your zero, otherwise the SQA will find out where you live and personally murder you. Now we'll do good old T. I'm wondering if we can get away with the same kind of slack behavior, but I think this. How many? That's 1, 2, 3, 4, 5, 6, 7, 8, 9. I've lost count. 1, 2. We'll just zoom out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we've got 13 of these spaces. So I'm going to do every 5 boxes is 0.0, 0.1. So it'll be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0, 1.1, 1.2, 1.3, 1.4, 1.5, 6, 1.7, 1.8, if I was good at drawing, 1.9 to, I don't think I need to list this, but I'll do it just in case. Don't want the SQA to hunt me down. Boom. And then we need to make sure we label this axis. So we have to say that this is t in seconds. Okay, so now we've got our axis down, we can actually start drawing points. So at 0.45, which would be on this line, it goes up, it's 1.6. So we can draw a point there. 1.6 is exactly there. So I'm gonna, there we go. 0.4, it's 1.56. So that would be down here, because each division upwards would be worth 2. So it'll be exactly there. And then another 5 will be down to 4. And then on here it would be in between, because it'd be 0, it's down to 1.53. And then it's the same for the next rung along. And then for 0.22, for some reason, because I had to ruin my whole brilliant plan, it jumps back up to 1.55, which is up here, and then 1.58 at 0.2, that would be there. Then we just join them up. And there you go. Using a graph, state 2 values of h that produce a period of 5, 7. I'll get rid of this now. So 0.2, we want to find 5, 7. So this top line here is 8. So 5, 7 is in between. So according to this graph, it's in between there. So I'm going to get my highlighter out. It's 1 there, and then 1 here. They're both in between stuff, so I'm reckoning that's 0.205, and then 205 h, and then now what looks like 1, 2, 3. That'll be like 0.425. Oh yeah, and this, I've messed with periods, but you know. There we go. So I'll go and fix that because that's pretty embarrassing. But all you need to know is that it's 0.205 and 0.425 h in meters. Right. Using a graph, establish the minimum period t. So that would be the look at this. Yeah, you draw this in a nice curve. Look at the absolute minimum it gets, which is about here, I would say. Which is roughly 1.53 seconds. I've skipped up a bit, haven't I? It's almost there, folks, don't worry. 0.53 seconds. Suggest improvement to experimental procedure that will allow a more precise value for the minimum period t to be determined. So what you can say here is you can say take more measurements near the turning point, because that's the That's the dip of the parabola. Yeah, so what I mean by this is you're going to have more measurements around here to get a more precise value, because as you hear, we kind of just joined it up kind of haphazardly. But if you actually went through, figure that out, you would get a better value. And, oh, you don't know how long I've been waiting for this. End of question paper. We just did solve this last problem. The quantities t and h are related by the relationship t squared h equals 4 pi squared h squared over g plus c. What on earth? Use data from the table, page 40, to calculate the value c when h is 0.3. A unit is not required. Yeah. Okay. So h is 0.3. So that means t would be, I've already forgot it, 1.53. Gravitational field strength, c is a constant. So, yeah, let's go and try and do this. So we want to get c, so I'm going to rearrange this equation to be t squared h minus 4 pi squared h squared over g equals c. So t squared is 1.53 squared. I'll put brackets around it just to be in case. H is 0.3. Take away 4 pi. Pi is a constant. 4 pi squared is a constant. H is 0.3 squared over g, which is 9.8, and that should give us c. So after we finish this monster of a calculation, we are free. Right, and now we're going to shove it into our calculator. There we go, so that's the first bit. Making sure I got all my brackets in there. So we take away, so 4 times pi squared times 0.3 squared, then divide by 9.8, and we get final answer c equals 0.339, so I'm going to round it up to 0.34. And there it is, folks. That is the entirety of the SQA 2019 Physics Higher Pass paper. Hope you enjoyed, at the very least tolerated, or at the very, very least didn't pull your hair out for the entire thing. I'll be back sometime with even more amazingly entertaining videos. But it's been Mash, it's been kind teaching you. Mash out.